Hey guys, welcome, I'm the Comet, and this is a video of me attempting to deeply explain how my circuit works. I expected a few of you to not believe it, so I hope that with this I'll be able to avoid any doubts you may have, because this is indeed legit. So in case you haven't seen the last video, I demonstrated a plasma speaker, which is essentially an amplifier that takes a small signal from any MP3 player and amplifies it to about 20,000 volts, which will be seen here at the spark gap. And the music I play on here will be audible from the spark. So let me just quickly do that right now. Plug it in. So that's the spark, and you don't hear anything right now because it's oscillating at a frequency higher than what we can hear. And here I'm gonna stupid thing. Okay, so here I'm gonna connect an audio source. Press play on that, and you can hear the music from the spark. And I can touch the spark with a screwdriver. As you can see, the music is actually coming from the spark gap, and I'm not hiding anything at all. So in this video I'm going to give a deep explanation on how the circuitry works, and hopefully some of you will be able to duplicate this circuit, make one for yourself. Okay, so I'll begin by explaining how it works very roughly with a block diagram, how it works and why, and then later on I'll move into more detail and show you my exact circuit that I used. So the basic concept of the plasma speaker is it's a D-class amplifier. So what happens is you have an audio source from your MP3 player. You amplify that a bit. You drive that through a chip which converts it into a pulse width modulated signal, which is just a square wave signal. That is then fed to a driver, and then that's driving the spark gap that you guys all saw in the video. So what is exactly a pulse width modulated signal? Well, you can imagine an audio signal from your MP3 player looking somewhat like that. It's just a bunch of sound waves all mixed together. Now, what the pulse width modulated signal is, it's a square wave, and what we do with this square wave, we oscillate it at roughly 40 kilohertz. So this is above what humans can hear, and that's why you couldn't hear the spark gap when I didn't connect any music, because it was too high for you to hear. So what we do with the audio signal is we change the time that this signal is on and off. So you can imagine a sine wave as our audio signal. And what's actually happening with our pulse width modulated signal is when this is high, we have the square wave stay on much longer than it's off. And as the sinus gets lower, we increase the time it's off and decrease the time that this square wave is on. So this square wave here represents the sinus modulated on top of it. So this is what the pulse width modulation does. Now I can actually show you guys this square wave signal. I'll just fire up the oscilloscope, and I'll measure the output on the coil and display it on the oscilloscope. Okay, so here's the square wave I was talking about. This is taken directly from the coil. The little swinging section here, that's just the inductive properties of the coil. So if I detach the coil, this would actually be a pretty nice square wave. So right now I have no music connected, so the square wave is just oscillating at 40 kilohertz, and that's what's making this spark appear. Now, as soon as I turn on the music, you'll see that the square wave is jittering. And what's actually happening is the music is determining the duty cycle of the square wave. So the music would match perfectly. You can actually see the music kind of at that area there. Now, the reason we can hear it from the spark is because what this is doing is it's causing the spark to either fire earlier or later. And the difference in firing causes the exact music to be heard from the spark, because whenever the spark fires, it causes the air around it to expand and contract. And yeah, that's pretty much how it works. That's the basic concept. Okay, so the first place to start would probably be at the audio input. So that's your typical audio jack. I found that the voltage that comes from MP3 players is quite small. The maximum we ever see is about 1 volt effective. So what I decide to do is amplify it a bit before I go to the pulse width modulation IC, just because the spark was too quiet. So in order to do this, we'll have to decouple the audio signal. That is done with capacitor and 2 resistors. I chose 10 kilo ohm for these and 10 microfarad for this one. With this signal, we can now go to the operational amplifier, which will amplify it. This is just your standard non-inverting amplifier. There we go. So I decided to amplify it by about a factor of 4. So for that, we need about 27 kilo ohms here and 10 here, because it amplifies by V equals 1 plus R1 divided by R2, which in this case is 1 plus 27 over 10, which amounts to 3.7, so almost 4. Now, it's important to note that we cannot connect this to ground, because the audio signal is now swinging around half of the supply voltage instead of around ground, which is 6 volts. So we'll have to connect this point to 6 volts as well. For this, I used another amplifier. Or more like an impedance converter, which gets its voltage again from 2 resistors. Here I chose 10 kilo ohms and 10 kilo ohms, so you have a nice 6 volts at this point. And this just makes sure that this point it always stays at 6 volts, no matter what resistance is at this point. I recommend connecting 2 capacitors here just to make sure it's stable. They don't have to be too big, probably 100 nanofarad, about around that place. So at this point we have a signal here amplified by 3.7, and it's swinging around 6 volts. In this next section we'll be looking at pulse width modulation and how we generate that signal. The chip I used for this plasma speaker is the TL494. It's a pretty popular chip. I've seen it used quite a bit in this area. So from the part before, we're receiving a signal swinging around 6 volts. So first thing we have to do is, of course, decouple it again. I chose 47 nanofarads for that. Then this is all from the datasheet recommended operation. So we go here to a trimmer, and I guess you guys just have to trust me on this part, because this is just how you configure. Then we have 2 pins. This can be seen in the datasheet. Pin 5 is where we connect the capacitor. This generates a triangle wave, and according to how big you choose this capacitor and how large you choose this resistor, we can set the frequency of the square wave. Just use a trimmer here so I can adjust the frequency afterwards. That's 22 kiloohms, and this is 2 kiloohms. And I chose 10 nanofarad for this one. Okay, so this IC automatically converts any analog signal to a pulse width modulated square wave. Now, what's actually happening inside this IC, if you're interested, is it's actually quite simple. We have a generator which generates a triangle wave. And what happens is this triangle wave is compared to the input signal. So this could be that sinus that I drew before. Well, that's ugly. Anyway, that's what happens. And if you see here, the higher that this voltage is here, the sooner this will turn off. So what happens here is exactly the pulse width modulated square wave. You'll get something like that. But this is all controlled by that IC, so you don't really need to worry about much. Now, I'm not quite finished with the pulse width modulation part, but we'll have to look at the output before we can go, and then I'll go back again to the pulse width modulation, because there's something we need to know about the output before we can continue. What I decided to do is to use just a simple MOSFET which will control the transformer. There we go. So that's one way to do it, and that's how I did it. Now, there's a much more powerful and more elegant way in order to achieve this, because here we're losing actually a lot of power, because whenever this turns off, there's an internal, or most of them have this internal Zener diode. Mine's at 100 volts. And all of that power dissipates on this thing, so this will heat up really, really hot. That's why I have that fan and everything. So this is actually a very inefficient way of achieving the spark gap. So I'm going to show you a way to do it very efficiently. So what I'm going to do is show you a full bridge driver. For this, I'm going to use another IC. This one here is the IRS 2104. Has 8 pins. One is the supply voltage, so obviously that one goes to the supply voltage. The input, we'll talk more about that later. This is the pin 3 is, just label these. Pin 3 is the shutdown pin, so we'll want that on high, so it's not shutting down. This one is the ground. Okay, Then on the other side, this one drives a MOSFET. Pin 6 is the sense pin. By the way, this is a bootstrap method. That just means that you can use 2 N-channel MOSFETs. So on the top we have another N-channel. There we go. Pin 7 drives that MOSFET, and pin 8 is the one that has to hold the coupling capacitor. So that goes like that. And you'll need probably a Schottky diode here, which goes to the supply voltage. And this here can go to your supply voltage as well. So essentially this thing, this IC, just controls the switching of these two. And what happens is either this one here is turned on and that one off, which means that this output will be on ground, or this one's off and that one's on, and then this potential will be at the supply voltage. Now, right now this is a half-bridge driver, so that means we have to do this twice. So I'll do that on the other side. You can just imagine it being here. I'll just draw the MOSFETs, and the IC is exactly the same, there's no difference at all. There we go. Okay, so these two go to another IC with the same setup as here. Okay, and that's actually almost it. Your coil is attached here, so your transformer, and this is where we'll have the spark. Now, the way this works is, this one's always the inverse of this one. So whenever this one is on and this one is off, this one will have to be on and this one will have to be off. Which means that the current is going to flow from here through the coil and through this to ground. Then what we do is we switch the two. So this one is on and that one is on, and these two are off. And then the current's going to flow in the opposite direction, so it's going to go down here through the coil and then down here to ground. This way we're driving the coil from both ends, and we're not really dissipating any power at all, so this is very efficient. Now, in order to be able to do this, we need a normal signal, which will come from our pulse width modulation IC, and we'll need the same signal but inverted in order to drive this side. So now that we know that, the IC is going to be here, going to have some wire which drives it. So we have two wires here. One has to have the normal pulse width modulated signal, and one has to have the exact opposite inverted signal of that one. So with this knowledge, let's go back to the circuit before. Okay, so in the datasheet of the TL494, there will be two outputs specified. These, there's some internal logic here, and it gives you two bipolar transistors, of which you have control of the collector and emitter. So we're going to use this to our advantage in order to create the inverted signal. So the first one, we're going to just connect this one to supply voltage, and then with this one we'll just go out. Now when this internal thing switches to 12 volts, we'll have whatever that is minus 0.7 volts, because there are always 0.7 volts from base to emitter. This doesn't really matter because that's high enough to drive the driver IC. So this is now going to swing at the non-inverted signal. I recommend connecting a resistor to ground, probably 5.1K, just because there's going to always be a small capacitance and there's nowhere for this voltage to really discharge when this switches to 0, so you'll need that. Now, in order to generate the inverted signal, it's quite simple. We just connect this into ground and use this one. Whoops, that's not really connected. Just imagine that this resistor goes to ground. Okay, actually I'll move it down there. No connection here. Okay, and what we do with this is we use a simple pull-up resistor, which goes to supply voltage. So with these two wires, we now have the pulse width modulated signal on both, but this one's inverted from that. And that's pretty much it. We connect these two wires to the driver, and that's the entire circuit. In order to transform the voltage to a high voltage, I recommend getting a car ignition coil or a flyback transformer or something that's used to generate high voltages. What I did with this one is I took away the primary winding, which was on it before, and made my own custom one with much less winding so I can get a much higher voltage at the very end. What you can do with our circuit, with the one I explained at the very end, with the full bridge driver, is you can connect multiple coils in series, in parallel I mean, and then hook the output in series. So if we look at that, just get a new paper. So if this is our output from our circuit, from our full bridge driver, we can connect the first coil like that, and we can connect the second coil screwed up like that. So these two are in parallel, and the secondary winding you can connect in series and you'll have double the voltage on the output. So thank you for listening to this long-winded and boring explanation of my circuit, and I hope to see more people make cool things like this. Thank you.